We can observe the fundamental physics of wave speed by setting up a race. We are sending two identical pulses down two tracks, a thick, heavy nautical rope on the left and a razor-thin steel wire on the right. The wire transmits the pulse instantly. On the nautical rope, the disturbance crawls forward, trailing behind. It's tempting to think we can force the rope to catch up. If we swing the hammer with twice the force, we might logically expect the wave to travel faster. It doesn't. No matter how much energy goes into the initial strike, the forward speed across the medium remains the same. This speed limit is a hard-coded property of the material. It is a constant that exists independently of the person shaking the string. The velocity of the wave is determined by a specific negotiation between two physical properties, the tension pulling the string taut and the mass holding it back. A guitar functions as a precision physics laboratory designed to control these variables. The thicker strings are manufactured to be heavier. This high mass density is a deliberate design choice, used to slow the wave down for lower notes. Instruments like the sitar rely on extreme length and high tension across the primary strings to achieve a specific resonant speed. The sharp angle of these violin strings crossing the bridge visualizes the restoring force, the physical pressure exerted by tension pulling the string back. To calculate wave speed, we use two variables. First, the tension, T. Second, the linear mass density, mu, which measures how much mass is packed into a unit of length. Every stringed instrument ever created is a different method of balancing these two competing forces to set a precise speed. Tension is the accelerator. It provides the restoring force, which is the string's elastic desire to return to its equilibrium position. Higher tension creates a faster snap. As the wave progresses, high tension forces each neighboring segment of the string to react more quickly, pulling the disturbance forward. The opponent in this system is the linear mass density, which acts as the brake. This is the physical inertia of the material. A heavy string moves slower because it has more mass that the tension must work to accelerate, causing a measurable lag in the wave's progress. Isaac Newton was among the first to move these observations into a scientific derivation, analyzing how waves move through elastic media. Finding the exact speed requires us to mathematically divide the accelerator, tension, by the brake, density. Through dimensional analysis, tension is a force, mass times length divided by time squared. We divide that by linear mass density, mass per unit of length. The mass units cancel out. The remaining units merge into length squared over time squared. Since velocity is measured in straight length over time, we take the square root of the result. This yields the final formula. V equals the square root of T over mu. This equation defines the speed limit of a transverse wave. It uses the internal properties of the material to predict exactly how fast energy will travel. This creates a final paradox. If speed is fixed by the physical properties of the string, what happens if you shake the string twice as fast? We look to the relationship V equals lambda times nu. Frequency is how fast you shake the string, while lambda is the wavelength. If the velocity is constant, any increase in frequency forces the wavelength to physically shrink to compensate. The arm generates more waves per second, tightly packing them together, but the leading edge still moves down the string at the same constant speed. The source controls the frequency, but the medium itself dictates the speed. Wave speed is the inevitable physical consequence of balancing a material's elastic pull and its mass. This same balance of restoring force and density determines how sound moves through air and how seismic waves ripple through the Earth's crust. Studying waves moving through strings provides the mechanical foundation for more abstract concepts, like matter waves. These waves are associated with the constituents of matter, like electrons, and allow scientists to use electron microscopes to visualize the subatomic world. Understanding these properties allows us to map the precise mechanics of how information and energy propagate through the physical world.